We have a circular conductor carrying current. In the previous class, we had a straight conductor carrying current. Now let us understand how is this conductor produce magnetic field in the space. We can apply the same method as we did it in the previous classes. The magnetic field lines are the concentric lines at every point on the conductor on the way around it. At every point on the conductor on the way around it, around the circle. Concentric circles. In addition to this, we have a magnetic line of force. It is always a straight line along the axis of the circle. This is the axis of the circle, the straight line passing through the center of the circle. Along that line, the magnetic line is always a straight line, and the direction of the magnetic field is from left to right. If the current in the conductor flowing in the anti-clockwise direction, look at that current direction in the loop, anti-clockwise direction, this is anti-clockwise direction. And this magnetic field, the field strength along the line, it varies. The value is maximum at the point. It decreases as you move away from this point, that is either in this direction or in that direction. About this concept, we can obtain a mathematical expression. That is what we are going to derive the mathematical expression for the magnetic field at a point on the axis of the circle. We need this geometry of drawings. That is a circle, a conductor of circular shape. That is the axis of the circle. On the circle, I am taking one point where I need to express the magnetic field strength. Anywhere on the point, I am taking the point at this point. This is a point where we need to express the magnetic field strength due to this current carrying element. So this geometry means in accordance with the Biot-Savart's law. That is the element. What is that? Current carrying conductor. As you know, you can divide the conductor into infinite number of parts. The conductor length is L. Total L is, that is circumference of the circle as L. Small l. Like this. This is the radius of the circle. I am taking one element, that is dl, that is infinitesimal value as dl, element of the current as dl. I am choosing this at this point. So you have to write the law. What is the law? In accordance with the Biot-Savart's law, the mathematical expression for the magnetic field at this point due to this element carrying current that is dl, is what is that? Recall this mathematical expression, mu naught by 4 pi into I dl sin theta by half square. I is the current strength in the conductor and dl is the length and r is the distance between the point and this point, that is dl, and this point p, and the theta is the angle between dl and r. Now what is the angle between dl and r in this diagram? This circle is lying perpendicular to the board but writing like this. So this is in the plane of yz, that is the y axis, x axis, and the z axis is perpendicular to this point like this. This line, this circular, is perpendicular to the board plane. Now if that is the case, that dl is, it lies in what is that, along the z axis. dl actually is lie along the z axis, and this line is lying in the xy plane. What is xy plane? That is the same board, plane of board. So that means if we talk about this, this is L in z axis, z direction. This is dl. That is dl. So this is r. This is dl. This is r. The stick is r. So this is in x direction. This is in the plane. What is that? Xy plane. So if you write like that, the line is what is that in different orientation. That is bending upward or bending downward like this. This is bending downward. The angle between this line and this line is always perpendicular. Look at this. Here. 90 degree. If that is 90 degree, so that is what I am showing, simple diagram here. The dl portion I have taken, that is element of current dl, and this is r. The angle between them is 90 degree. This is 90 degree but bending towards the x axis. Now it becomes sin theta, sin 90 is 1, we reduce to this equation. That is in accordance with Biot-Savart's law, dB at this point. Now it is a three-dimensional geometry because this is in one plane and these lines are in one plane. If that is the case, what is that? At this point, magnetic field, as you know, it is a vector. What would be the direction of the magnetic field? In accordance with the same law, Biot-Savart's law, magnetic field, that is, these two lines are perpendicular. Magnetic field line is also perpendicular to this line as well as this line. What is the direction of the line like this? So you should not draw a line perpendicular to this line. If this is perpendicular, this also perpendicular to this line because it is z direction. That is z direction. Look at this. These two lines I am drawing. This line is a magnetic field direction due to this element. This is a position vector. These two lines are perpendicular. Again, you see that this is x axis, this is y axis. These two are perpendicular. As you know, coordinate Cartesian, that is coordinates x and y are perpendicular. This line and this line are perpendicular. This line and this lines are perpendicular, and these lines are the same plane. There is a board plane, xy plane. If this line makes an angle with this is pi, because I am using pi, already theta is used. Then this line with the y axis should make angle pi. Like this. Because these two are perpendicular, these two are perpendicular. This is about this element. I am taking another element exactly in the opposite point, opposite direction, the same conductor. With this element, you get a similar type of geometry for this as well. Look at this. That is, this is R, this is dl, and this is magnetic field. It should be perpendicular to this line, like this. This dB is due to this element, this dB is due to this element. The magnitude of the field at this point, it is also depending on the direction of the orientation of the field, because it is direction to orientation of field is phi. This phi is same here. If phi is different, magnitude of magnetic field at this point also difference. So for that we need, what is that? This is the vector. What is the magnetic field vector? Now we shall resolve this vector into its two components, vertical components. Recall that resolving a vector into its vertical components. One is along x-axis, other along y-axis. As you know, this is a phi angle making with y-axis. This is y-axis. So if that is the case, when we resolve this line into two vertical lines, there is y and x. If this is dp, what are their vertical components? Along y-axis, it is dp cos phi, because this angle line is making a theta, that is angle with this y-axis. So it becomes, what is that, adjacent side, and this becomes opposite side. If you have a triangle, to write the components, dB cos phi is the vertical component along y-axis, and dB sin phi vertical component along the x-axis for this vector. So this is resolved into these two vectors components. In a similar fashion, let us resolve this vector into their components in the same fashion. If we do so, we get, what is that? This is dB cos phi, this is dB sin phi. After this, we have to understand what is the direction of the magnetic field. It is, of course, along the line. Whether it is away from the point or towards the point. Here I am going away from the point. How do you write this? To understand the direction, recall what is the right hand palm rule. What is right hand palm rule? Now I am taking this conductor, circular conductor. That is what I am taking the conductor. And the current in the conductor is, I said, in the anti-clockwise I am taking. Anti-clockwise, this is the direction, anti-clockwise. So what is the orientation of this circle? Actually, this is orientation for perpendicular to the board, like this. Center is here. All these lines are on the board plane. So what is right hand palm rule? That is, at this position holding the direction is hold with the right hand, so that the thumb gives a direction of the current. This is the direction of the current, and remaining fingers curl around the conductor like this. To understand the direction about this point, look at that first holding that here like this finger, always move the curling fingers like this at this point. That is concentric circle. But these, what is that, curling fingers, there are movement of the curling fingers. Look at that. So here movement of the curling fingers like this, come here like at this point. What is the movement? This is a direction. That is a direction is away from the point. This is how you can understand the direction. What about at this portion? The same conductor. Here the current is like this. like this. So I am holding, should hold the conductor like this. So the direction is like this. Hold with the right hand, thumb in the direction of the current, and remaining fingers, what is that? Make a movement like this. This is a portion. Curling fingers are making movement like this. Here. Come here at the point. Here. Away from the part. This is why direction should be straight line. Direction is this side or this side. Like this, you understand. So with this point, we have resolved into vector. Two vectors, and direction is this, direction is this. If this is the direction, what are their components? Should be away. Components direction should be like this. Here also component direction like this. X component, Y component. So that's the direction of the magnetic field away from this point. So at this point, one more important point you need to understand. With this, these two components are in one line, but in the opposite direction. That is cancelled. This vector is getting cancelled by this vector. Opposite direction, same line. Component, these two components are zero at this. What about these two components? These two components are in the same direction. These two components will add up because same line now will add up. So the component by this will add up along this. Not only you have these elements, you have infinite number of elements. There is also there. So we have infinite number of dB sin phi along the x-axis. For a total amount of field, you have to add up all those elements. That is dB, infinite numbers are there. So sum of the infinite number of these, it is same as one more mathematical concept, is the integral of the function. dB, infinite number of values. Integration of dB sin phi. What is B? Total amount of magnetic field at this point due to this current loop is given by this integration sign, that is dB sin phi. And dB is, what is that? We get this value or expression using Biot-Savart's law. dB is same thing. You can write. And what is sin phi? That is depends on the direction of current. Phi is here, phi is also here. You have to express sin phi in the form, what is that? In the form of, that is parameters what we need. The parameters are and R. For that, you have to take this phi, the triangle is right angle triangle, sin phi is opposite by hypotenuse, R by R. What is R? Capital radius of the circle. What is small r? That is case. Bigger case, smaller case. Distance between the point and this point. Radius, position vector. So this is sin phi. This is, we get this and this from this geometry of drawings. And this is from the Biot-Savart's law. Put all of them into this equation. Write the value for this using Biot-Savart's law, and this is using this. So equation 2 and 3 into the equation 1. Same equation, simplify. Integral of this is dB, this is sin phi. In these functions, all of them are constants except dl. With this particular, what is that? Current loop, carrying current I. So it's the integral of dl. What is the integral of dl? So it is dl is small n, total length is l. That is from 0 to l. Total length is l. Total length, it is also called as circumference of the circle, 2 pi r. R is the radius of the circle. So this dl is 2 pi r. Integral of dl is 2 pi r. Simplify, r becomes r square. 2 pi, 4 pi cancels, 2 remains, and r cube in the denominator. So b equals mu naught into I r square divided by 2 r cube. And also we can have substitution for r as well, because you know there is a right angle triangle. Apply Pythagoras theorem, that is r square is equal to r square plus x square. What is r? Root of this. It is same as power 1 by 2. So substitute for r into is. So r is this, to the power of cube is, that is 3 by 2. So final expression is, mathematical expression is this is what we get. B equals mu naught I into r square divided by r square plus x square 3 by 2. So this is what the mathematical procedure for the derivation of the expression B. That is, B is the magnitude of the field strength at this point. It is depending on, directly depends on the current strength in the conductor and the radius of the conductor, but inversely related to the distance between the point and the center of the circle. This. With this you can write the possible cases. If x equals 0, x equals 0 means when the point comes here, the point is at the center of the circle. Let us see what is the expression we get. Substitute for x equals 0 and simplify. That is 0. This 0 is r square to the power of 3 by 2. 2 cancels, 3 remains. R square, r cube is here, cancellation, r remains. Final expression is mu naught I divided by 2r. This is the magnitude of the magnetic field at the center of the circle. It is a maximum value for that conductor. If the point is moving away from, that is from the center away towards infinity, infinite distance, then x equals infinity. Let's say x equals infinity. Here look at the denominator and put x equals infinity. Infinity plus anything is infinity. Infinity into infinity, anything is infinity. The denominator is infinity. So 1 by infinity is 0. That is why b is 0. The value of b is 0 at infinite distance. So the minimum possible value is 0. Maximum possible value is this value, I by r. So that is what the case. I said no. The magnetic field is maximum at the point. It decreases, becomes 0 at the infinite distance. Either you go either this direction or this direction. Now I written what is this direction of the magnetic field, that is line. What is the direction? Direction is from left to right if the current is in the anti-clockwise direction. What is this geometry I have written here? Same current loop, anti-clockwise. I am taking a point this side, left hand side, where the point is right hand side. Whether you take the point on the right hand side or left hand side, you draw same geometry. If you draw same geometry on the left hand side, there is a line, straight line, perpendicular to this is the line. Straight line, perpendicular is magnetic lines, perpendicular to this line here. And again, what is that? These are the y axis and x axis. And in this case, what is that? You have to understand what is the direction. This straight line. What is the direction? Here, direction is towards the point. Direction is towards the point. How do you write again? right hand palm rule. You have to apply right hand palm rule. I am taking this and holding the same conductor. The same conductor. Yes, here anti-clockwise direction. At this position, you have to hold like this. Current direction, thumb direction. Hold it like this, and make the movement of the curling fingers. Look at that. This is the conductor. At this point, I am holding movement of the curling fingers like this. Look at that. The direction is towards the point. This is how we can find the direction. What about at this element? At this element, this is what is the same anti-direction is. This is the direction. You have to hold the conductor like this with right hand. That is the direction of the current. That is the make a what is that curling fingers movement. At this point I am making movement. So move like this. That is direction is, look at that, towards the point. So this is the one very important to understand. Writing line, what is the direction? So direction is towards the point. If this is the point, what is that? What is that? It is a vector. If you resolve this vector into what is that y direction, y and x axis is dv cos theta, dv sin theta. If this is the direction, what is their component direction? It is same, towards the point, towards the point. Here also towards the point. These two are towards the point, dv like this. And again at this point, these two are getting cancelled, lying in the same line but in the opposite direction. Opposite means towards. It is moving towards here, moving away. The only difference. Opposite direction. Here getting cancelled. Only thing, these values are added up, but in the same line. So this is the direction. Whether you take the point on the right hand side or left hand side, is the direction like this. So it is understood. If this is the case, variation moving from this point to this point, direction of the magnetic line of force, it is a direction from left to right if the current is in the anti-clockwise direction in the loop. This is the graphical representation of the variation of B along the x-axis. Here now moving from x-axis along the x-axis. So it is from the infinity towards the 0 and here towards the infinity. As you move along this x-axis, the B value increases gradually, reaches the maximum at the center, and then move away from this point. It again decreases, becomes 0 at the infinite. So this graphical representation is variation of B due to loop current along the axis. That is the graphical representation. So this is what the concept, and one more will be the direction. So now I have told you, if the loop current direction is anti-clockwise, loop current is anti-direction, what is the possible direction of the magnetic field? I don't know, left to right. Look at the line. For this current carrying loop anti-clockwise, the magnetic lines are left to right direction. So this straight line along the axis, and if you move away from what is that in a circle only, here the lines are bending. I said concentric lines at every point like this. Lines are bending, but the direction is same, left to right, left to right. This is also important to indicate the magnetic lines and their direction with respect to the loop current. If the current direction reverses in the loop, this is anti-clockwise. If it is clockwise direction, magnetic lines are also reverse. For this it is clockwise direction, magnetic lines of force from right to left. Along the axis, it is away from the axis, bending like this. That is a diagram. Geometry is showing magnetic lines of force due to this current carrying conductor. That is the one. And last one. So the expression what I have derived here, it is for only one turn, only one wire. If you increase the number of wires, number of turns, for one turn, this is the value. For two turns, one more turn of the same radius, magnetic field along the axis doubles. For three, triples. For n number of turns, n times. Same expression, multiply with n. It is a magnetic field along the point for n number of turns. That is the expression. The same thing at the center. This is what it says. At the center, if you have n number of turns, you have this into n. So remember these equations. So what are these equations? Mathematical expression for B for one turn and mathematical expression for B for n turns. Just multiply with this n. So these are the equations we need. What is that? Remember to solve the problems. So with this we have completed today's portion. Thank you very much.